Small animals and insects like caterpillars can articulate their body segments with 3 degrees of freedom. However, realization of 3-DoF motions in small robots is a challenge due to limitations in actuator technology. In this work, we concede full 3-DoF motion and instead design a mechanism to produce a one-dimensional curve in SO3. We achieve this task with a spherical 4-bar linkage. Using an optimization algorithm, we compute the dimensions of a spherical 4-bar that approximates a set of desired end-effector task positions. We apply this procedure to the segment articulation mechanism by specifying task positions, computing candidate solutions, and selecting a linkage. The synthesized mechanism has a pure yaw region, which exhibits deviations of 35 degrees on either side of the straight position, and an upwards pitch region, which reaches an angle of 40 degrees. The same procedure was used to design a pro-leg mechanism for the Caterpillar robot segments. The mechanisms were implemented in a modular Caterpillar robot. Each segment contains only 2 brushed DC motors. Segments are chained together with compliant grippers. The segment articulation mechanisms are used to steer the robot by rotating in the pure yaw region of motion. The compliant gripper on each segment can be opened by actuating a shape memory alloy through electrical heating. This allows the robot to reconfigure into chains of various lengths, which can each move independently. Segments can be reconnected by opening a gripper and positioning it within the receiving slot of another segment. Cooling the SMA closes the gripper and connects the 2 segments. The unoccupied gripper on the front of a caterpillar chain can also be used to pick up and manipulate objects. Positioning the gripper around an object is done with a combination of pro-leg motion and segment articulation. Microspines embedded in the gripper help to maintain a good grip. To lift objects in the air, such as to reach a tall bin, segment articulation mechanisms are rotated into their upwards pitch region. By separating into smaller chains, the robots can work together to achieve tasks more efficiently. Here, 2 3-segment chains work together to pick up small pieces of trash. Articulating segments can also be used to overcome obstacles. The robot is able to climb onto a 2.5 centimeter step and transition from flat ground onto a 30-degree incline. Microspines embedded in the foot of each pro-leg engage with the ground, which keeps the robot from slipping. With many sets of legs and a single chain, the robot is able to maintain good contact with the ground while climbing inclines.